In the past 90 days, a single object has rewritten what we thought we knew about asteroids. It moves like no rock should move. It brightens without warning, and it's heading inward on a trajectory that defies every model we've built. Surveys tracked it for years as a harmless space rock. Then everything changed. This is not just an orbital anomaly. It exposes how little we understand about what lurks in the asteroid belt, and it raises questions that challenge the very definition of what an asteroid can be. What are we really looking at as 31 Atlas accelerates toward the inner solar system? A digital clock ticks forward. October 3rd, 2025, 1847 UTC. In the Data Processing Center, the Asteroid Terrestrial Impact Last Alert System, called ATLAS, an operator reviews the night's photometric measurements. A flagged entry appears on screen. Object designation 31 Atlas. The brightness readings are off. In just 72 hours, the object has jumped 1.2 magnitudes brighter, a surge that should not happen to a bare rock drifting through space. Coordinates are verified. The object sits at 2.89 astronomical units from the Sun, deep in the main asteroid belt between Mars and Jupiter. It should be stable, cold, inert. But the light curve tells a different story. A second alert triggers. Motion vectors show a subtle but measurable acceleration, non-gravitational in nature. Something is pushing 31 Atlas. The Minor Planet Center receives the anomaly report within hours and issues Circular MPC 2025. T94, flagging the object for immediate follow-up. But by the time the notice reaches observatories worldwide, 31 Atlas has already begun its most dramatic transformation yet. The numbers are logged with precision. Heliocentric distance, apparent magnitude, rate of brightening, delta V deviation from predicted orbit, all captured in the cold language of astrometry, yet all pointing to something unprecedented. The orbital reconstruction tool pulls up 31 Atlas's discovery data from February 2019. Back then, it was just another among millions, cataloged as a main belt asteroid with a semi-major axis of $2.64 and an unremarkable albedo. For 6 years, it behaved exactly as expected. Observations came in regularly. The orbit refined. The predictions held. There was no activity, no coma, no tail. Just a 4-kilometer wide rock following Kepler's laws with mathematical certainty. The playback advances month by month. Through 2020, 2021, 2022, all quiet. Then, in September 2023, a single observation notes a minor brightness fluctuation. It's dismissed as instrumental noise, a bad pixel, atmospheric distortion. The next check, 3 weeks later, shows nothing unusual. The anomaly is forgotten. But now, rewinding and enhancing those archived images, a faint haze appears around the nucleus. Barely perceptible, easily missed. The first sign that 31 Atlas was waking up. Fast forward to June 2025. A routine survey pass catches the object mid-outburst. In the span of 48 hours, it brightens by 0.8 magnitudes and develops a faint dust envelope stretching 15,000 kilometers across. Spectroscopic follow-up reveals emission lines, water vapor, cyanogen, dust grain scattering sunlight, chemical signatures identical to those of an active comet, not an asteroid. The classification changes overnight. What was once filed as Asteroid 31 Atlas is now reclassified as Comet 31P/Atlas. But the new label only deepens a mystery. How does a main belt object, frozen for billions of years, suddenly start behaving like a comet? The discovery of cometary activity in 31 Atlas is not an isolated case, but it pushes the phenomenon to new extremes. Astronomers have known since the early 2000s that some asteroids can harbor ice and occasionally show comet-like behavior. These objects, called main belt comets or active asteroids, occupy a gray zone between traditional classifications. The first confirmed example, 133P/El Pizarro, was discovered in 1996, displaying a faint tail despite orbiting squarely within the asteroid belt. Since then, fewer than 30 such objects have been identified. What makes 31 Atlas alarming is the intensity and persistence of its activity. Most main belt comets show brief, weak outbursts triggered by impacts or rotational stress. Their comae are faint, their tails short-lived. 31 Atlas, by contrast, has been actively outgassing for months, releasing material at a rate comparable to some Jupiter family comets. Spectroscopic data collected by the Very Large Telescope in Chile reveals emission bands for CN, C2, and OH radicals, classic markers of sublimating ice. But the object's location, far from the sun and embedded in a region where temperatures should keep water ice locked solid, makes this activity difficult to explain. Standard models assume that main belt objects exhausted their volatile reservoirs early in solar system history. Billions of years of solar heating should have driven off any surface ice, leaving only inert rock and metal. Yet 31 Atlas has a dust production rate exceeding 100 kilograms per second, sustained over multiple orbital passes. Some researchers propose that subsurface ice deposits, shielded beneath meters of insulating regolith, have remained frozen since the solar system's formation. A recent impact or internal stress fracture could have exposed these reserves, triggering the sudden onset of activity. But the numbers don't quite add up. To sustain this level of outgassing, 31 Atlas would need to contain a significant fraction of its mass in ice, far more than expected for a body that has spent 4.5 billion years in the warm inner belt. Alternative explanations invoke exotic volatile species, clathrate hydrates, or chemical reactions driven by solar wind interactions. None fully account for the observed behavior. The reality is that 31 Atlas operates on the edge of what current models can accommodate, and each new observation pushes it further into uncharted territory. Dr. Jessica Agrawal, a planetary scientist specializing in active asteroids, leads an international team studying 31 Atlas. Her research group at the Max Planck Institute has been tracking the object's light curve since the first outburst. In a recent video conference, she described the challenge. We expect comets to be active near the sun. We expect asteroids to be dead rocks. 31 Atlas is neither and both. It's forcing us to rewrite the boundaries. Her team's analysis reveals a pattern. The outbursts are not random. They correlate with 31 Atlas's rotational phase, occurring every 8.7 hours when a specific region of the surface faces the sun. High-resolution imaging from the Hubble Space Telescope, obtained during a narrow observing window in late October, shows asymmetric jetting. Material streams from discrete vents near the object equator, not from a diffuse surface glow. This suggests localized ice deposits, possibly concentrated in ancient impact craters or fissures that have remained cold and dark for eons. But there's another anomaly. The jets don't just produce dust and gas. They exert force. Enough force to measurably alter 31 Atlas's trajectory. Preliminary orbital fits show a non-gravitational acceleration vector aligned with the jet direction, similar to the rocket effect seen in active comets. Over the past 4 months, this thrust has shifted the object's orbit by nearly 200 kilometers, a tiny deviation, but one with potentially significant long-term consequences. Dr. Agrawal's concern is clear. If 31 Atlas continues to outgas at this rate, its orbit will become increasingly unpredictable. We use asteroids following fixed paths. This one is steering itself. The implications ripple outward. If other dormant main belt objects harbor similar ice reserves, the population of potentially active bodies could be far larger than anyone suspected. And if those bodies can change their orbits, the entire framework of long-term trajectory prediction comes into question. November 12, 2025, amateur astronomer Michael Chun in Pasadena, California, sets up his 14-inch Schmidt-Cassegrain telescope in his backyard. He's been following 31 Atlas since the first report surfaced on the Comet Observer's mailing list. Tonight, conditions are perfect. Clear skies, low humidity, minimal light pollution. He centers the object in his field of view and begins a series of 5-minute exposures. By 02:30 UTC, Chin has stacked 18 frames. What emerges on his monitor stops him cold. The comet's coma, already well developed, now shows a faint streak extending northwest. A tail, not the broad, diffuse fan typical of dust tails, but narrow, almost linear structure pointing away from the sun. He checks his processing. No artifacts. No stacking errors. The tail is real. Within hours, confirmation arrives from observers in Australia, Japan, and South Africa. Independent images, different equipment. Same result. The tail has appeared suddenly, growing from nothing to a feature 50,000 kilometers long in less than 24 hours. Photometric measurements show another brightness spike, this one more abrupt than any before. In just 6 hours, 31 Atlas surges by 0.9 magnitudes, visible now even through binoculars under dark skies. The amateur network lights up. Forum posts multiply. Time-lapse sequences are shared, debated, analyzed. Some speculate fragmentation. Others suggest a massive new outburst. A few wonder if the object has collided with something, triggering a catastrophic release of subsurface volatiles. Professional astronomers scramble to secure telescope time, but the object is already fading again. By November 15th, the tail has dimmed to near invisibility, and the brightness has dropped back to pre-outburst levels. What caused the sudden flare? No one knows. The event was too brief for detailed spectroscopy, too localized for most surveys to catch. Only the vigilance of the amateur community, eyes on the sky every clear night, captured the full sequence. Once again, distributed observers have documented a phenomenon that might otherwise have been missed entirely, adding another puzzle piece to the growing enigma of 31 Atlas. Mid-November brings a development that shifts the conversation from scientific curiosity to potential threat. Orbital dynamics specialists at NASA's Jet Propulsion Laboratory run updated trajectory models, incorporating the latest astrometric data. The new fits account for the non-gravitational forces, the jetting, the subtle but persistent rocket effect. When the simulations propagate forward, a troubling picture emerges. 31 Atlas's orbit is evolving. Slowly but measurably, each outburst nudges the object slightly inward, reducing its perihelion distance, the closest point to the Sun. Over the next decade, if activity continues at current levels, the comet could migrate from the main belt into the inner solar system. Preliminary impact probability assessments are run. The numbers are small but non-zero. A 1 in 50,000 chance of an Earth intersection by 2037. A 1 in 8,000 chance by 2045. These are not imminent threats, but they represent a fundamental shift in how 31 Atlas is classified. It is no longer just a scientific oddity. It is now on the watch list, flagged as a potentially hazardous object pending further observations. The reclassification triggers automatic alerts to international space agencies and planetary defense networks. Observing priority is elevated. Radar campaigns are scheduled. The object that was once a footnote in the asteroid catalog has become a subject of active monitoring. Dr. Paul Chodas, director of the Center for Near-Earth Object Studies, issues a measure statement. 31 Atlas presents a unique challenge. Its behavior is unpredictable, and our models are still catching up. We're not sounding alarms, but we are paying very close attention. The subtext is clear. When an object can change its own orbit, standard risk assessment tools break down. Every new outburst recalibrates the threat level. Every jet reorients the trajectory. The uncertainty compounds with each passing month. Dr. James McCanney, a physicist known for his unconventional views on comets and solar system dynamics, sees 31 Atlas as evidence of something deeper. In his perspective, comets and active asteroids are not simply ice and rock. They are electrically charged bodies interacting with the sun's plasma environment. When 31 Atlas brightens and jets material, it might be responding to fluctuations in the solar wind, drawing energy from the electric field that permeates space. McCanney points to the timing of the outbursts. They don't correlate perfectly with solar heating alone. Some occur when the object is still too far from the sun for thermal sublimation to fully explain the activity. He suggests that electric discharge, a kind of cosmic lightning, could be triggering localized explosive events on the surface. This would account for the sudden, intense flares in the narrow, structured jets that don't fit standard volatile-driven models. While mainstream astronomy remains skeptical, the electric universe hypothesis raises questions worth considering. Could some cometary phenomena involve plasma interactions we don't yet fully understand? Might the boundary between chemistry and electrical dynamics be more fluid than our textbooks suggest? McCanney doesn't claim to have all the answers, but he argues for keeping an open mind. As 31 Atlas continues to defy expectations, the possibility that we're missing a piece of the puzzle, something related to charge, field, and flow, lingers at the edge of the conversation. The scientific community is mobilizing. Dr. Amy Mainzer, principal investigator for the Near-Earth Object Surveyor mission, advocates for enhanced detection capabilities. 31 Atlas slipped through the cracks because we weren't looking for activity in the main belt. We need infrared surveys that can spot thermal anomalies, not just visible brightness. We need all-sky monitoring that doesn't assume asteroids are inert. Recommendations are forming into action plans. Expand survey coverage to include the entire main belt, not just nearer space. Deploy space-based infrared telescopes capable of detecting temperature spikes that precede visible outbursts. Integrate machine learning algorithms trained to flag unusual light curves and motion patterns in real time. Establish rapid response protocols that can trigger follow-up observations within hours, not days. The amateur community is also stepping up. Coordinated observing campaigns are organized through the International Astronomical Union's Minor Planet Center. Citizen scientists are urged to monitor 31 Atlas and similar objects, providing the high-cadence data that professional surveys often lack. Crowdsourced photometry is proving invaluable, filling gaps and catching transient events that would otherwise vanish unrecorded. The message from planetary defense advocates is urgent but pragmatic. We cannot predict what 31 Atlas will do next, but we can be ready. More eyes, more instruments, more data. Preparation, not panic. Vigilance, not complacency. The solar system has shown us a new kind of wild card. Our response will determine whether we're caught off guard or ready to adapt. Right now, a single object in the asteroid belt is rewriting the rules, challenging our models, and hinting at a solar system more dynamic and dangerous than we assumed. Our detection networks are improving, but gaps remain. As 31 Atlas continues its unpredictable dance, the urgent truth is clear. We are observers of forces we barely comprehend, navigating a cosmos that does not wait for permission to surprise us. The boundary between asteroid and comet has blurred. The line between predictable and chaotic has shifted. What do you see when you look up at the night sky?